Hello everyone. Let's quickly understand what we are going to do in this particular course. So these are the three main areas I'm going to cover in this particular course. First and foremost, we will try to understand what is Merkle tree is all about by understanding its theory, its core concept. Once we have the theory in place, we will go and try to implement Merkle tree in vanilla JavaScript. And finally, once we have implemented Merkle tree in vanilla JavaScript, we will identify where this particular powerful data structure is used in real world softwares and applications. And that's where we talk about real world use case, right? So what you need or what I expect from the students are the following. We should be aware of basics of JavaScript. I expect Node.js to be installed because I pick the runtime for JavaScript as Node.js in this particular course. And of course, you can choose your favorite text editor, but I might stick to WebStorm, but the choice is completely yours. So this is all you need, and this is all the agenda that I have for this particular course. Hello everyone. In this particular lecture, we are going to understand Merkle tree in theory. Merkle tree, even though the name sounds complicated, in fact it's very simple to understand. Merkle tree in fact are also called as hash tree, and the core algorithm or core concept behind this Merkle tree is this. This tree hashes its leaf node from bottom up till it reaches the parent. This text might be a little bit confusing, so I have taken the Merkle tree representation image from Wikipedia to go through with you. Let's imagine we have 4 data blocks. You might be wondering what the data blocks might be. It can be string, it can be number, it can be bytes, it can be an object, it can be anything. For now, let's imagine they are numbers. So we have numbers L1, L2, L3 and L4. All right. Now, each content in the data block, in this case the numbers, should be hashed. So we hash L1 into hash of L1. All right. And we do the same for L2, L3 and L4. So we get hash of L1, hash of L2, hash of L3 and hash of L4. As we have seen from this particular text, the tree fundamentally hashes its leaf nodes from bottom up till it reaches the parent. So what does that mean is that even though we have done with the hashes of these data blocks, we need to do until you reach the parent, right? So what we have to do in the next step is we have to take the hash of L1, take the hash of L2, combine them together and then hash it. So let's call this as hash of 0 and do the same on the right hand side of the tree. Take hash of L3, take hash of L4, combine them and then again hash into hash of H1, right? And finally, now we are left with 2 nodes, all right? Hence, again we need to do the process with the same step. You take this hash of 0, you take this hash of 1, combine them and again do a hash. That is the root of our entire tree, and this is in very simple way what Merkle tree does. Of course, we have used this term hashing quite a bit in Merkle tree. In fact, Merkle tree completely depends upon the hashing algorithm that we pick and choose while we implement or write our code. And that's the exact reason we are going to discuss in a little bit of examples what is hashing and how one can write hash functions in vanilla JavaScript. Thank you. Hello everyone. In this particular lecture, let's understand what are hashes. So I'm just going to pull over my WebStorm. You can just pick whatever ID or whatever favorite text editor of your choice, but yeah, it's up to you. So what I'm going to do is I'm just going to give you an example of what is hashing in a very simple term. So let's get started. So fundamentally, hashing is just that, given an input, all right? So let's assume you are given an input of text called test, okay? You need to take this input and convert into something which cannot be, found that, this is the value, all right? So for example, I'm just converting text to something like this, all right? Or I can convert text to some random number. But the catch here is that given this number, no one shouldn't identify this particular value is coming from the input with the value called test. Okay, so this is the fundamental idea behind hashing. All right, so let's go and implement a very simple hashing. Of course, this is not production ready hashing, so I'm not going to recommend this way of hashing in any production ready code. All right, so I'm just going to create a function called hash, which takes a argument called string. All right, so what I'm going to do is I'm just going to get each characters in the string and going to get its character code. So you might be wondering what is character code. I can just explain you in a moment. Let's assume I'm just going to write a for each over here. I'm going to write for let of I is equal to 0, I less than string dot of length, right, and I plus plus, right. Now what I'm going to do is I'm just going to create something called constant of hashing. All right, sorry, I'll just create as let of hashing is equal to empty string. This hashing variable would be storing the result of the hashed value of this input string. All right, what I'm going to do is I'm just going to do hashing, all right, plus equals. All right, I'm going to do string dot I'm going to use this method called coded character, sorry, char coded. All right, so this particular method is available in the string prototype, which would give you the character for any given string, sorry, which would give you the number for any given character. All right, so what I'm going to do is I'm just going to use this particular function, okay, with the value of I. That's all. Okay, now let's return this hashing, okay, and test it quickly with hash of, let's say, test. I'm going to run this one. Okay, it didn't return anything, so let's quickly see what is happening over here. Okay, so I'm going to just quickly debug this one and let's understand what's not happening. Okay, I'm just returning the hashing string core character at I. Okay, it's 16. Okay, oops, I guess it returned, but I forgot to do the console.log, so I'm doing this one over here. So now we should be able to if you remove the debugger, we should be able to see the output as this whole string. All right, so we can call this particular function as hash, but there are a lot of caveats in this implementation, as we just started this lecture with the understanding that given this particular number, no one shouldn't able to identify its input. Now we can clearly see that for each character we are taking the char coded, which means we are taking the numerical value of t, which is like 116, numerical value of e, which is like 101, numerical value of s, which is again 115, and numerical value of t, which is 116. Now a hacker or a genius person can identify this output of our hash function and come to a conclusion that this particular value is nothing but the input test. All right, and that is something the hash function shouldn't allow in production world use case. All right, and that is where we are going to understand what is called as a one-way hashing. All right, let us go back to the slide and see what are they. All right, so the one-way hashing, or what we call it as a cryptographic hashing, solves the exact problem that we have seen. Now given any input, it gives you an output which cannot be retraced. So fundamentally one can see the output and cannot justify or cannot guess the value of its input, and it's impossible to get the input from the output. And also one of the important characteristics of the cryptographic hash function is that it gives the same output for the same set of input, even if we call multiple times. All right, of course we are going to see and run through examples of particular hash functions while we're going to implement the Merkle tree. But yes, this is the whole idea behind cryptographic hashing. All right, you might be wondering, like, what are different types of hashings available in today's market, right? There are different type of hashings. We call it as like Tiger, MD2, CRST32, SHA1, 512, MD5, and so on and so forth. In this particular implementation of Merkle tree, we will be sticking to SHA 256, which is coming directly from the node module. All right, so I hope that in this lecture you understood what is hashing, what is one-way hashing, and how one-way hashing is also called as cryptographic hashing. In the next lecture, you will understand, what is the main benefit of hashing, and like why we need to come up with a code which just hashes a string into something else. Like, what benefit do we get? All right, so that's exactly the topic of our next video. Thank you. Hello everyone, let us quickly understand why we need hashing in first place. Well, in the last video, we saw what are called as cryptographic hashing and one-way hash functions. We also tried to implement a very simple hash function, but learned from our mistakes that, by seeing the output, one can detect the input, which is wrong in a real-world use case. You might be wondering why hash is actually used in real-world softwares or applications. There are a lot of use cases for hashing, and for instance, hashing is something that is in fact used in Merkle tree, as we saw in earlier videos. But at the same time, if you think hashing in general, they have so many use cases. I'm going to pick you and walk you through one of the use cases where hashing is really helpful. All right, as we saw in last video, there is this special type of hashing called MD5. Now what I'm going to do is I'm just going to run MD5 hash from my terminal for this particular file. Remember, file is nothing but a bytes, or you can consider that as a sequence of streams. What I'm going to do is I'm just going to open up my terminal. Right, I'm in the hashing folder, which has hash.js, and I'm on my Mac machine. So technically speaking, I have MD5 already within my Mac machine. If you are using Linux, I hope so it should be available, but for Windows users, I'm not sure like what is the available hash within the Windows operating system, but that's fine. I'm just going to give you the gist of the uses of hashing, or why we need hashing in first place. I'm just going to use this command MD5, and I'm just going to give the input as hash.js, and I'm just going to press return. And if you can quickly notice, it just gives you a long string. This is what we call it as a hash value for this given input hash.js. In fact, this input is nothing but the whole content of this file. All right, as we talked in the earlier video, if we change the input, it should generate a completely a new hash value, right? So what I'm going to do is I'm just going to delete this line and save this file. All right, and now again I'm going to go to the terminal and run md5 hash.js. You can quickly see the output, or the hash value of hash.js is also changed. Now you could able to see that from this hash value, no one can identify, okay, this E9A blah 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 is actually our little hash function with so and so comments. No one can do that, right? And that's the power of hashing. And to quickly see, it produces the same hash value for the same input. I have redo my deletion, and I'm going to run the same command again, and you can quickly see the same hash value is repeated for the same input. Well, all is good. Now imagine we are going to send this hash.js from your machine, let's call this as server 1, to your friend machine, let's call that as server 2. All right, what we can do is, in fact, while we send hash.js, we also calculate the checksum. So what is checksum? Checksum is nothing but the hash of this particular file, or any file. All right, so I'm going to use md5, okay, and I'm going to calculate hash.js. For instance, this is the hash value. I'm going to send two things over the networks. One is hash file, okay, the content of the hash itself. Along with that, I'm just going to send the checksum, all right, which is nothing but our hash value, so that on the receiving end in the machine S2, rather than trying to look into this file in first place, it can quickly check the checksum. Okay, so it can quickly compute hash.js, okay, on the server 2 by again running md5 of hash.js, okay, which should give you the same value, right? If that is the case, both the machines or the softwares can come to a conclusion that the file that is transferred over the network, in this case hash.js, is not corrupted. It's a quick win for both the parties. All right, so the corruption can be of multiple reasons. There could be a issue in the network transformation, or it could be a issue in your data blocks in your hard drives and things like that. But just calculating the checksum at each end and sending it over the network allows one to quickly check the data integrity and also check the data for corruption in matter of seconds. Of course, you have seen clearly that MD5 could able to give you the hash value in a very small amount of time, and that's the power of hashing. Of course, there are lots and lots of use cases of hashing, and that's what we are going to see by implementing Merkle tree and going to see how Git uses hashing and Merkle tree in order to produce a beautiful software that we use in our day-to-day life. But of course, this is one of the use cases of hashing, but there are a lot of use cases. But I hope I have given you a gist of why hashing could be useful in real world scenario. Thank you. Hello everyone. In this particular lecture, we are going to implement Merkle tree. I've just created a brand new file in JavaScript called tree.js, and for reference, I have just kept the Merkle tree in a pictorial representation so that we can write code by looking into this particular image. Again, this is image that I got from Wikipedia. So let's get started. So I'm just going to declare a class called Merkle tree. Okay, so what do you need in this class? So those things I would be like putting up in the constructor, right? So let me also just zoom a little bit in so that the font is much more visible. Okay, so in the screenshot of the tree structure, if you have a close look at it, you can able to see that we need to have a name for the particular node. All right, and also we need to store the content of that particular node, and we also need to know for example, this particular node we need to know like which is the parent node. All right, so we need name, content, parent, and also we need the levels. So levels is something that will be required in the in future videos, but level is nothing but like at what level the tree is. For example, this is level 0, level 1, level 2, and level 3, and so on and so forth until you reach the leaf of the tree. So we need these many variables to store in our class. So that is name, content. I'm going to keep level, and whether the tree the node is having a parent or not. Okay, so all this I'm going to just store it in under this particular instance. This dot name is equal to name, and this dot content is equal to, I'm going to just create an empty content for the nodes that are created brand new, and also I'm going to do this dot level is equal to the level that is given by the user. Okay, and finally this dot parent is equal to parent. All right, and we also need one more important thing called children. If you remember, each node can contain children, right? So children are nothing but like number of nodes it directly connects to it, right? So for that instance, I'm just going to keep the instance variable called children, which is going to store an empty array. All right, so now all the data that is required to store the tree is present, but also at the same time we need to write functions or instance methods which will allow the users of this Merkle tree to add say for example content. All right, so for that what I'm going to do is I'm just going to define a function called set content, which will take the content. All right, and it just sets set dot of content is equal to content. All right, as simple as that. Okay, and at the same time let's say if you want to add a couple of children, I mean like couple of nodes to a parent, you definitely need a method, right? For example, if you want to add hash of 0 and hash of 1 to top hash node, definitely there should be function, right? So that function is something, let's go and write. So I'm just going to call that function as add of child. Okay, and I'm just going to take the upcoming request with the argument as node. And what I'm going to do is as simple, I'm just going to do this sort of children dot of push of the node. Okay, remember, whenever a node in the Merkle tree is constructed, we are going to have its children as an empty array, and if someone is going to call add of child, I'm just going to do this sort of children dot of push of node. Perfect. Okay, and let's go and quickly test this one. I'm going to create a node. Let me call it as root, and I'm just going to do a new of Merkle tree, and I'm going to set its name as a root node, and I'm just going to set the content as root. Okay, I guess this content should be set as it is rather than the empty string. I guess that's an issue over here that is changed right now. And level, since it's going to be the parent, which means I'm just trying to create this parent node over here, so its level is going to be 0. And since this is the top of our whole Merkle tree, what I'm going to do is I'm just going to leave the parent as it is, so that this dot parent for this particular root would be empty or undefined. Okay, now that is in place, I'm just going to create a couple of child. I'm going to first call it as child1 Merkle tree, and I'm just going to call of child, and going to do of child1 content. And now I'm going to set the level of child based upon the root dot of level plus 1. Okay, so root dot of level is nothing but 0. I'm going to get that one and do the addition as plus 1. So logically, all the child or children that belongs to root would be one level higher than that, right? So I'm going to do the same thing for child 2 quickly over here. It's going to Merkle tree. I'm just going to do call as child 2. We can call child 1 as child 1, and now I can just go and do child content. Now again the same thing, root dot of level plus 1. Okay, that's awesome, right? Now what I'm going to do is this. Okay, now if you think about this, we should add both child 1, okay, and child 2 into the root, right? For that, what we should do is I'm just going to do root of add child. That is something that we've written on line number 15, and I'm just going to do child of 1, and I'm going to do root of add child of 2. That's all. I'm just going to do a console log of root, and I'm just going to run the script in the debug mode. Okay, and I'm just going to attach a debugger on line number 27, and let us see what's happening. Okay, I pause the debugger. Let me retry it again. So root, okay, so if you notice it here, root has couple of children, both are of instance of Merkle tree, and it contains child 1 and child 2 whose content is also set properly, and the level is also set perfectly. You could able to see the issue over here. The Merkle trees child 1 and child 2's parent is set as undefined. So what we should do over here is we should do set the parent here. Okay, parent, it's going to be root, and it's going to be root. Okay, and if you rerun it, now both the child parent would be pointing back to the actual root itself. So fundamentally what we have done is we have created a Merkle tree with 3 nodes. So technically node 1, which we call it as root, child 1 and child 2. Now both child 1 and child 2 are connected to this particular parent. Okay, now I believe now it's the right time to introduce you to the hashing concept, right? If you remember from this image and our previous discussion, whenever the child is added or the child content is changing, we should calculate the hash function, so that you calculate hash of child 1, calculate hash of child 2, combine them to form the hash of the root, right? So that is something we need to do in the upcoming lectures. Thank you. Hello everyone. In this particular lecture, we are going to talk about cryptographic hash functions, and very specifically, we are going to talk about SHA 256. Just a quick recap from our previous lectures. We understood that there are cryptographic hash functions which are also called as one-way hash function, who can just take an input and spit you out an output, and there are like multiple variations out there in the market, but with our implementations for Merkle tree, we are going to pick SHA 256. Okay, so SHA 256 is a one-way cryptographic hash function which we can use to get the hash of any string or any other content. Okay, I'm going to just give you a very simple code snippet that just showcases how one should use Node.js inbuilt module called crypto in order to use this particular cryptographic hash function of SHA 256. All right, so I've just created a crypto.js file, and yeah, let us go and just pull out the crypto module. So crypto, and I'm just going to use require of crypto. Okay, and what I'm going to do is I'm just going to do crypto dot create hash. Okay, and the first algorithm, I mean like the first argument is the algorithm. I'm just going to say SHA 256, and I'm just going to chain this function with update function. Okay, and update function is where you generally give the content of which we need to run the hash against it. Okay, I'm just going to do test something. Okay, and I'm just going to do that dot digest of hex. So digest of x will give you the actual hashed value. All right, so I'm going to store this in let of result is equal to this one, and I'm just going to do console.log of result. Okay, in order to run this program, as I've said earlier, you need Node.js, and once you have that in place, you can just run node space crypto.js, because you know this crypto module is coming from Node. So let us go quickly and run crypto.js. Here we go. This is the output that we get. Okay, perfect. Now if you remember, if you try to call the same function with same content, in this case this content is going to be test something, the result is going to be the same thing. Okay, so maybe I can just do let of result 2, and over here I can just run console.log result triple is equal to result of 2. So fundamentally this should print true. Perfect. Now let's go quickly and also change the content a little bit, which means this should in fact return false. Okay, perfect. And this is a very simple example of SHA 256 usage with inbuilt Node crypto module. Awesome. To just give a gist of what this 256 is all about, whereas SHA is the algorithm name, 256 is where it just spits out the hash function with 256 bits. Okay, and there are like other variations like SHA 512 and things like that. Yeah, to just give you that information as well. Now let's pull out the existing Merkle trees image. Now if you understand from our earlier videos, we need to hash the content whenever a node is getting added or whenever a node is getting changed. All right, and that's what we are going to do. Now what I'm going to do is I'm just going to take this particular code that we written in crypto.js, and I'm just going to put it into a utility function called generate hash. Okay, so generate hash will take the argument as content, and it does run SHA 256 and returns it. Okay, and remember I just need to import it as well, so I'm just going to do crypto is equal to require of crypto. All right, perfect. Now what I should do is we should calculate the hash function whenever a node is getting added or whenever a node is getting changed, right? So a node will get added via the constructor function in our case. So what I'm going to do is I'm just going to do this dot of hash. I'm just going to keep a instance field called hash, and that would be nothing but using this generate hash function, and this would take our stringified version of all these values. Okay, it's going to take name, it's going to take level, and finally it's also going to take the content. Okay, so content would be nothing but this sort of content. All right, perfect. I guess for content also we can leave as it is. Yes, perfect. So let us quickly run this code and in debug mode and see what is happening for root. Okay, so root would be having the hash of this particular value, because when you call this line number 30, this would get called, which in fact calls the SHA-256 algorithm to generate the hash value. All right, perfect. Now going back to the image, we should also run the hash function whenever a child is getting appended to any root or any parent, right? So which means what I'm going to do is I'm just going to stop this execution for now. Inside add child, what I'm going to do is I'm just going to do this sort of hash is equal to generate of generate hash. And now what I'm going to do is I'm just going to do this sort of get child hashes. Okay, let's talk about this child hashes for a moment. So the whole purpose of get child hashes is this. Imagine we have our Merkle tree with only two nodes. One is root and one is one child one. Now, when someone is attaching another node into our Merkle tree, else imagine hash of 1, what we should do is we should get the hash value of this particular node and also get the hash value of this particular node, combine them together. That's what forms the hash of the root, right? And that's exactly what get of child hashes will do. Let's go back to the code and do that. What I'm going to do is I'm just going to do this sort of children, okay, because I'm going to get the root children and call our JavaScript function reduce. Reduce would give two arguments, which is like the accumulator, which I'm going to call it as previous, and the current value, which I'm going to call it as current itself. Now what I'm going to do is I'm just going to do with the accumulator, what I'm going to do is I'm just going to accumulate everything that is coming from the current, which is nothing but the hashes of the children, right? And the initial value I'm going to pass it as an empty string, and I'm just going to call return. That's all. So what it does is it runs over all its children, get the current hash and append it, so that when someone adds a new child into any tree, the tree's root hash would also get updated. Okay, now add child, that with the implementation of get child hashes, it's done. Okay, now let us comment this line number 40. Okay, now let us run console.log of root.hash. Okay, and let me run this one, tree.js. Here we go. This is the hash for our tree, which has only one node. In this case it is child one, right? So basically our tree looks like this. So we have root, and inside root we have our child. Okay, and this root hash is nothing but this one. Okay, and child hash would be the one that is calculated by our SHA-256 algorithm, which can be like xxx. Now what we're going to do is we are going to uncomment this particular line child2, right? Which means like we are going to add this child2 into the root. Exactly correct. So what we should do is child2 is going to add it, okay, with its own hash. So what does that mean is, for root is that it needs to get its children, in this case child1 and child2, okay, and get its hash value of both the children, okay, which is like xxx and another xxx, and combine them to update the hash value of the root. That's exactly what this get children hashes does. This dot children dot of reduce, get the child1 hashes, which is xxx. So previous would be containing xx on the first iteration, and on second iteration it's going to append xx, and maybe we can term it as yyyy for easier understanding. So it's going to be yyyy. So the root dot hash would be something this one, right? So that's what going to happen. I'm going to rerun this code, tree.js, and you're able to see that now the hash of our root with two child is getting changed. That's the exact reason we have coded our get child hashes. We need to add one more function into our code base, is that whenever someone is calling set content to update the content of any node, we should recursively calculate the hashes, and that's exactly what we will do in the next lecture. Hello everyone, welcome to the lecture updating hashes recursively. In this lecture, what we are going to do specifically is that we are going to finish up our little function called set content. In order to understand why set content is essential, I'm going to create yet another node. We call it as child3, and going to append it as child of child1. Okay, so what I'm going to do is this. I'm just going to copy this one, okay, and I'm just going to paste this, but I'm just going to do child3, and let me also change the same over here, child3 content. Now rather than child3 is child of root, I'm going to set the root for child3 as child1. Okay, and that's all I'm going to do. And what I'm going to do now is I'm just going to do child3 dot add child, and I'm going to no, it's child1 dot of add child of child3. Okay, so fundamentally our tree looks like this right now. Okay, so we have root, and we have child1, and we have child2. Okay, and the child3 is nothing but a children, or I mean like a child of child1. Okay, this is how our tree looks like. Let us quickly go and let us quickly go and run our hash. So this is a hash function. Definitely the last time the hash was starting 684 character. Now the hash of root is something like this. Okay, the change is mainly because we have added the child3 into our Merkle tree, which would fundamentally trigger the change. Right now, we have a little function called set content, which one node can use this to change the content. Right now, let's imagine child3 wants to change the content to something else. Okay, something like this. Okay, child3 wants it to change the content to hey, I'm changing. Okay, now if you run this code right now, fundamentally we are getting the same hash, which is wrong, right? In fact, what we should have done is we should set the hash of the new content. In this case, it's hey, I'm changing, and propagate the change to child1. And since child1 is changed, I should get its parent and combine these two things to update the root hash, right? So fundamentally, when any one of your child or any one of your node changes, I should propagate the hashes recursively till I find the root node. That's exactly what we are going to do in our set content function. All right, set content. So this is basically does the content to the instance variable. Now we should update the hash, definitely. So I'm going to call generate hash function that we have done earlier, and I'm going to do JSON of stringify, and I'm just going to pass this object. Okay, so let me just make the code a little bit look good. Okay, this is perfect. Now I'm just going to do type of this sort of type, comma, and I'm just going to pass this sort of name, comma, and I'm just going to pass level of this dot of level, and finally I'm going to pass this content as this sort of content. Okay, perfect. Now I have generated the hash of this particular set content node, right? Even if you just go and run it, you would be still seeing the same value, right? So what we are going to do is we are going to propagate the change in this particular child tree to all the nodes in the Merkle tree. Okay, in order to do that, what I'm going to do is I'm just going to write a function called update hash to or else let's keep it as update children hashes. Okay, That's exactly what I'm going to do. And what I'm going to do over in set content is I'm just going to do this sort of parent dot update children hashes. Oops, update children hashes. Perfect. Okay, now in children hashes, what I'm going to do is I'm going to do this sort of hash is equal to generate hash using all the child nodes, which is like get child hashes, correct? Because imagine I'm updating the content of child 3, which means I need to check whether child 3 has any children and append it, right? So for that, I'm just going to call this generate hash by calling a utility function this dot get child hashes, correct? Once that is done, what should I do is I should check whether this dot parent is available. If it is present, I should do this dot of parent dot update children hashes. That's all. What I'm trying to do over here is I'm propagating the change from child 3 to its parent, and then again I'm calling the get child hashes to combine these two hashes and propagate again to the root until we reach a node whose this dot parent is null. Okay, now let us go and rerun this program. Now here we go, the hash of our root is completely changed. So you can play around by adding so many child or so many roots with different leaves and things like that. This is our complete implementation of Merkle tree. And yes, so that's all. Good job, folks. We have completed one of very good data structure that is available in place. In the next section, what I'm going to do is I'm going to introduce you how Merkle tree is used inside our famous tool Git, and how we could implement a very minimal Git from scratch using our Merkle tree. Hello everyone. In this particular lecture, we are going to understand update children hashes and set content method by running our example in debug mode. This is essential because this particular function update children hashes is very crucial in our Merkle tree concept. So what I've done is I've taken the code sample from our previous lecture and I've attached the debugging points or breakpoints in the places where it is actually required. I'm going to run in debug mode, debug tree.js, and it is getting stopped and get child hashes. I guess this can be resumed, and now this is getting stopped on line number 31 inside the function set content, right? So now here this refers to child 3. Okay, if you look at the current tree structure that we have drawn inside this particular comment over here, child 3's parent is child 1, right? So here this can be verified quickly. This sort of parent dot of parent dot of name is child 1, correct? Now what we do is we come to update children hashes, we generate hash for child 3. Okay, this is the hash. Okay, and what we do is we check whether this dot parent is present. In this case, this dot parent is present. Okay, and we do this dot of parent dot of update children hashes. Okay, now the second time when update children hashes is running, so this would be child 1. Okay, because we navigated from child 3 to child 1, right? Now child 1 has a leaf node of child 3. That is the exact reason we are calling get child hashes to calculate the hashes of child 3 in order to incorporate into the child 1, right? Now again I'm going to resume the program. Okay, now this dot this would be root because child 1's parent is root, right? Now root has two child 1 and child 2, which in fact can be the hashes can be calculated by calling this dot get child hashes, and that's exactly what is happening on line number 35. And remember, for this particular root node, this dot parent would be undefined. So that means this particular line would be false, and since this is false, we won't call this dot parent dot update children hashes again, which would end our program fundamentally. So I'm going to resume this one. We are calculating roots children again with the updated content hashes. So again, this can be verified over here. So this is nothing but root node. This dot children over here is nothing but child 1 and child 2. Remember, child 1 hash would have been changed. Again, primarily the reason is child 3's content is changed. And that's what we meant in earlier lectures, that we are propagating the changes from child 3 till we reach the root of our Merkle tree. And that's it. The output is same as earlier. Thank you. Hello everyone. Welcome to the section Merkle tree in real world. So in this particular video, what I'm going to do is I'm just going to give you a very short introduction about Git. So Git, technically speaking, is just a tool which allows you to manage your source code or any set of files. All right. So I'm just going to run you through a very simple example of how Git is and what is it's actually used for. For that reason, what I'm going to do is I'm just opened up my terminal. I'm just going to create a test directory. Okay, and I'm just going to inside the test directory, and I'm going to do git init. Okay, so git init, what it does is it initializes the git as a, it initializes the needed objects for git in order to track any changes in your test directory. Okay, fundamentally git is nothing but changes tracking tool. All right, so once you run git init, you could able to see that it initializes the git repository in this particular folder. Okay, now what I'm going to do is in this particular folder, I'm going to create a file. I'm just going to say, hey, this is my first file, and I'm going to call the file name as test file. All right, you can able to see the test file got created, and the content is, hey, this is my first file. Now, if you run git of status, Git is very clever enough to say that, there is a new file that is called as test file is created in this particular directory, and it is not getting tracked. Right now, let's say if you go and add git of test file and then run git of status, what it says is that I see something, a new file called test file, and it's again not yet committed. So in Git, commit is nothing but saving your work. Okay, you can compare git commit with respect to Microsoft Word or any text editor, command s or control s. You're saving your git in a particular state. Okay, when I say git of commit of -m test commit, this -m is nothing but I'm just giving a message to Git saying that save this particular state of my directory with the tag or commit message called test commit. Okay, then if you go and run git status, it says everything is clean, I've saved your entire directory and you are good to go. Now let me open up the test file. Okay, and I'm going to do remove a particular word from the test file, and I'm going to save this. Now if you run git of status, it says your file is modified, and the modified file is test file. You might be wondering, this is the whole purpose of Git, to track what is getting changed within its initialized Git repository, or we call it as initialized Git folder. Now this is where things gets a little bit interesting. The Git uses Merkle tree in order to track the changes in any particular folder. All right, so what we are going to do in this particular section is that we are going to implement a very minimal version of git add and git status. Okay, by using the Merkle tree that we have created in our previous section. So let's get started in the next lecture by writing our Merkle tree in order to implement our first mini git. Hello everyone, in this particular lecture we will try to understand how Merkle tree helps Git to identify the changes that have happened in the directory. If you remember from our earlier lecture, Git is really worried about what is exactly happening within the directory. right? It can be addition of file, it can be a deletion of file, it can be the content change in a particular file. We need to think how Merkle tree solves the Git's problem. The main agenda of Git is to identify these many changes, correct? Now we have our Merkle tree with one key important aspect, right? If you remember from our earlier discussions tree.js, what we are actually doing is we are calculating the root dot of hash fundamentally from all its children, correct? Now let us stop for a moment and think how Merkle tree can help Git. In Git, what it wants is, imagine this is the directory structure that is available in Git, and let's imagine L1, L2, L3, L4 are files, right? If someone is changing the file L3 in Git, when the developer running git space status, it needs to tell the developer that L3 is what changed. Now this is easily achievable by Merkle tree. The reason is that if L3 is changed, definitely the root hash will change. Of course, we need to write another utility functions or algorithm to identify what within the root has changed. That's a different story, but fundamentally Merkle tree has the exact requirement or exact powerfulness of identifying if anything within the tree changed very quickly, right? It can be L4, it can be L2. Even let's say someone is deleting this particular directory hash of 1 of 1, what would happen is that it would trigger the entire hash to be recomputed, which would result in change of root dot of hash, correct? So Merkle tree is a perfect use case for Git. In fact, if you go through the Wikipedia of Merkle tree introduction or documentation, it clearly mentioned Git uses a specialized version of Merkle tree to track the changes within the repository. And it's really good thing to understand how beautiful it is to use Merkle tree to solve the famous problem of what Git solves today. So in the next lecture, what we are going to do is we are going to take our tree.js and modify it so that it fits into our Git world. Hello everyone. In this particular lecture, what we are going to do is we are going to take our Merkle tree where we left off in the last lecture and try to create our mini Git and see how Merkle tree is used inside Git to track the file changes. Okay, so what I'm going to do is I'm just going to copy this particular class and I'm just going to go and create a file called Git. Okay, and I'm going to paste the code over here. Again, let me just go and make the size a little bit big. I'm going to call this class as Git rather than Merkle tree to just for easier understanding. And we need the crypto modules as well, so I'm going to copy this one into the top of this file. Okay, perfect. So nothing much. I've just moved the code between the files. All right, so fundamentally there are a couple of differences that I want to talk in this course. They are, okay, so Git fundamentally supports two things. One is directory, okay, and one is file, right? So fundamentally a directory is something you can think of as a root node which can contain multiple files. All right, and again a directory can contain as many directories. So a directory can contain another directory, which can contain a file or a directory, right? So this is something that we need to model within our class Git. Okay, so what I'm going to do for that is I'm going to bring a special type called type, okay, inside the constructor. Okay, so this type would clearly specify whether the file that is getting added or the content that is getting added, whether it's a directory or a file. Okay, I'm going to do this dot of type is equal to type. Okay, remember we are just modifying Merkle tree's core algorithm or data structure to fit for our Git use case. Okay, so yeah, so underlying data structure remains as Merkle tree, and what I'm going to do is I'm not going to calculate the hash for directories. because directories are nothing but a simple empty space which can contain files and which can contain additional directories, right? So what I'm going to do is I'm going to check whether the type of the incoming data, if it is a file, then I'm going to do a hash, else I'm going to keep the hash as an empty string, which means I'm going to keep the hash as empty string for directory type of data. In order to do that, what I'm going to do is I'm going to write a util function. Okay, over here I'm going to call the function as isFile. IsFile would take the type, right, and it's going to return, if type is file, it returns true. Okay, it's a very simple util. So what I'm going to do is I'm just going to use the util isFile and pass the type over here. Okay, and if the type is file, I'm going to generate the hash for directories which would fall back into this else block. I'm going to just keep this dot of hash is equal to empty string. Okay, for even we can leave the comment as for directories. Okay, perfect. Now similarly, we want to make the change in add child. Okay, if you remember from our previous Merkle tree discussion, add child doesn't care like what type of data is getting added. Like whenever a data is getting added via this add child method, we are going to regenerate the hashes and things like that, right? We need to have a separate util very similar to isFile. I'm going to name it as isDirectory. Again, it's going to take the type. Okay, if type triple is equal to directory, okay, I'm going to say it as, return it as true. Quickly, what we can do is we can refactor this code as this one so that it can be reused else. Okay, this is good. So I'm going to remove this code over here and also this one here. Okay, now what I'm going to do is I'm going to add the check over here. So if not of directory, okay, I'm going to return it. If is not directory, okay, I'm going to return. Yeah, so basically I'm very much interested in adding a child only if it is of type directory. Okay, so that is one thing. And other thing is that I need to do the same thing for set content, right? For set content, I'm just going to generate the hash only for the files, not for directories. Okay, if not of isFile, okay, this dot of type I'm going to return. Okay, whereas in the add child, what I'm saying is if it's not of directory, I'm going to return. In set content, I'm really worried about generating the hashes only if it is of type file. Okay, perfect. Now what I'm going to do here is this one. Okay, generally whenever if you save a file in a Git environment, it just gives you a hash. Okay, so that hash I'm going to store it in a variable called committed hash. For now, for all the data that is coming into our Git instance, we'll be having the committed hash as an empty string. Okay, perfect. So what I'm going to do right now is this. I'm going to expose a method called commit, very similar to Git. What it does is it just says this sort of committed hash is equal to this sort of hash. So fundamentally, if you remember, each node will be having a hash based upon its content. That's what we use in our earlier discussions. So this commit function, what it does is it takes the hash and sets it to the committed hash. Okay, and I'm going to recursively check if it is a directory with this sort of type. I'm going to recursively do this sort of children dot of for each child. I'm going to do child of commit. Okay, what I'm doing is this. Okay, let us go back to the image. If someone is calling a commit on the root node, I'm going to check whether the root is having a children. If there are children, I'm going to call commit on that children as well. So what does that happen is that if this particular node is having another children, it goes and calls the commit of this particular node. So fundamentally, when someone is doing a commit of the root node, I'm taking all the hashes that are available already on the node and setting those hashes, setting those hashes back to my variable called committed hash. So I've just made few changes or incorporated Merkle tree with our requirement to implement our mini kit. So with this in place, what I'm going to do is in the next lecture, I'm going to implement a couple of methods which will allow us to visually see how Git works. Hello everyone. In this particular lecture, what we are going to do is we are going to implement a couple of methods called status and print tree. So before doing that, I'm just going back to my terminal to understand how Git actually works. So what I'm going to do is we are already in the test directory. If you remember, we have one file called test file, and I'm going to run git of status. All right, now git of status says everything is clean on this particular branch. What I'm going to do is I'm just going to open this test file and I'm just going to randomly add some content. And now since the test file is changed, I'm going to run again git status, and it says the modified file is test file. So fundamentally, Git is able to identify the file that is changed within this repository is called a test file. Definitely, we also need a particular flag within our Git instance to identify, a file is modified or not. So I'm going to keep that variable as, modified. Right now, what we are going to do is we are going to add this test file into Git and going to run again status. It says it's modified and it's good to be committed. So what I'm going to do is I'm just going to run git of -m committing again. Okay, now if you run this, okay, and run git of status again, it says again everything is clean and everything is saved on this particular repository, right? So fundamentally, the modified flag is now not available within Git because everything is saved properly. If you run git of log, you could able to see there are two commits. One is the commit with 80, another is a commit with 62b, right? So this is the last commit that we have done. If you remember from our earlier lecture, we had commit method within our Git class, correct? This committed hash that we introduced in last lecture is nothing but this hash, right? So again, if you run git status on a repository where there is no more changes detected by Git, it's going to return everything is clean, correct? So in that situation, what we should do is we should go and make sure that this dot of modified is equal to false, correct? And remember, commit is going to run on every node that is available in our Merkle tree. Okay, so with commit in place and with modified new flag in place, I'm going to implement the status function. So status is going to take an argument called parent. Okay, so remember again in our Merkle tree, there will be a node whose parent is undefined, correct? So I'm going to add a if check over here. So basically using the or operator, if parent is present, well, it's well and good, else I'm going to take the current instance and I'm going to check whether node.of_hash not equals node.of committed hash. Okay, so fundamentally what I'm trying to do is the current hash of any node, whether it is equal to the committed hash. If you remember with our actual Git, if someone does the commit operation, the hash of both the node and the committed hash will be made equal. So if that is not the case, it means there is a change in our file system, right? In our Git repository, correct? So that is where what I'm going to do is I'm going to pull back the modified flag that we have defined earlier and set that particular node modified as true. So fundamentally, line number 75 and 76 are nothing but if the hash which a node is not equal to the committed hash, I'm going to call that as modified as true. Okay, and remember, we need to do the same thing again for the entire node if it's a directory. So I'm going to do if it's of directory, and I'm going to do node of type. Okay, and since it's a directory, if you remember, the node will be having a children, so we can go and get node out of children for each of node. Okay, and so over here I can just call it as n. Okay, sorry, yeah, this sort of status as n. Okay, perfect, nothing fancy over here. So what I'm saying is just rerun the status in all the nodes. So let's say if someone is running git dot of status on this node, go and check if it is of type directory. Yes, if it is of type directory, go and check if it has any children, fundamentally if it has any files. If that is the case, go and check whether this particular file hash is equal to committed hash or not. If not, is change it, and do this until you reach a point where there is no parent, which means the root node, right? That's it. So now with commit and status, and also with the modified instance variable in place, what I'm going to do is I'm going to write a function called print tree. Okay, the print tree is essentially required to visualize how git our git works, very similar to how the actual git prints the modified file in the color way and things like that, right? So, and that's the essential purpose of this function. Okay, I'm going to pull out a couple of variables. This would make sense while we write the code. What I'm going to do is I'm just going to create a function called function of print tree of root. Okay, and what I'm going to do is we need a function to perform the indentation, so that we could able to see the directory with right indentation, and it's easy to track which file is under which directory. And I'm going to write a for loop over here, I less than root dot of level. If you remember, each each node in our Merkle will be having a level are nothing but this is level 0, level 1, level 2, level 3, and so on and so forth until we reach the leaf node. So I'm taking and running over the root dot of level, and for each level I'm going to pull out node process stdout dot of write slash of t. For each level I'm just performing the indentation, nothing fancy over here. If the root dot of type is equal to directory, okay, directory is nothing but a string, and if root dot of name not is equal to directory name, what I'm going to do is I'm going to do the indentation of root. Okay, and this is the important point. So basically, if I'm checking if root dot of modified, okay, and if it is modified, what I'm going to do is I'm just going to print with a color code. Okay, for which I'm going to use control dot of log and paste the color code as it is. I've just taken the color code from the wiki page. This refers the yellow color code, and I'm just picking up root dot of name. So fundamentally, if a node is modified, I'm just printing it as the yellow color. Else I'm going to print the root dot of name as it is. Okay, so, and finally this particular block is essentially to check if it is a directory, and if it is not a new directory that is traversed. So I'm just saying directory dot of printed is equal to false. Okay, and I'm just going to set the directory name is equal to root dot of name. So fundamentally, this directory name keeps the current directory that is getting looped over. Okay, and the whole idea of line number 92 to 101 is just to print the directories with indentation, and also check if the directories have changed. If so, set the directory name with yellow color. Now with directories in place, I'm going to go ahead and do root dot of children dot of for each of child. For each child from the node's children, I'm going to check whether the child is of type file. Okay, If it is a file, again I just need to do the indentation. Remember, indentation is just mainly for our visual representation, and I'm going to perform the same thing as it over here. I'm going to check if child is modified. Okay, I'm going to print with the yellow color, else not. I'm just going to print it with this one. Okay, for the file name alone, what I'm going to do is I'm going to print it with the string called file name. Okay, so I'm going to put something like this. Okay, file name of yellow color, else it's just a simple string of file name. Okay, and this is the code for printing the child. And if again, if in one of our iterations we find a children if in one of our iteration if we find a child which is of type directory, we need to recursively call print tree. So I'm going to check child of type is equal to directory. Okay, what I'm going to do is I'm going to do print tree of child. Okay, so print trees again will get called. Okay, now in that case what happens is that the directory name would be changing because the current directory name is will be different. So it will enter this particular block, again check it, and make sure we are printing the directory only once using this particular flag. So that's all. Now with our mini git in place, what we can do is in the next lecture we can just test it. Hello everyone. In this particular lecture, what we're going to do is we are going to test our little git which we implemented using our Merkle tree algorithm. So let's get started. I'm going to write constant of root is equal to new of git. Now we need to pass the type directory because root is going to be directory, and now the second argument is nothing but the name. I'm just going to keep the name as root directory. And if you remember, since the change of our git constructor, I don't think so the content should be available for directory, right? So let us go quickly and change it. For all the node that is of type or directory, content should be logically empty. So I'm going to set this as empty, and also remove the content from here. Okay, and change it over here so that our generate hash function is happy. Okay, now that with that in place, since this is a root directory, I'm going to give the level as 0. There is no parent for it. Either you can give as undefined or null, or I prefer to leave it as it is. Okay, and I'm going to create another directory called second directory. Okay, and in which I'm going to create an instance of git of type directory, and I'm going to call as of second directory, and it's going to be a root dot of level plus 1, and that's all. Okay, and what I'm going to do now here is I'm just going to create a file. Okay, new of git of file type, and I'm going to name the file as test file. Okay, and I'm going to attach this file directly to the root directory. Okay, so which means I'm just going to do root of level plus 1. Okay, and I'm going to do of root. Okay, and that's all. Right, so now what I'm going to do next is I'm going to call set content. Basically I'm just going to set the content of this particular one with some data. Okay, now with that in place, I'm also going to create another file. Okay, before that I guess we can just go quickly check it. So fundamentally I'm going to do root of add child. I'm just going to do a file. Okay, and now I'm going to run root dot of status. Okay, and I'm just going to call print tree of root. Okay, let us go run this code. Oops, there is a failure. Okay, I guess I misspelled it earlier, so it should be std out, so that is in fine. So run it again. Okay, here we go. So our git able to identify that we have added a new file called test file. That's what is representing over here, whose content is some data. And since this particular file is not committed, our little git is very clever enough to print the entire directory is not committed either, and that's the reason it shows the yellow color. So what we should do in order to make the thing commit, so let's go and run git of commit. Okay, root.of commit. Okay, so this commit would now make all the hashes of the node to the committed.of hash. Now if you rerun it, you shouldn't be seeing the yellow color, which means our file or our git in the repository is fundamentally saved. Okay, now let's go and add some little bit complex use cases with addition of file2. Okay, I'm going to do git of file, and I'm going to call this file as hello world, and I'm going to attach this file again to root.of level +1, and I'm going to root. Okay, and finally I'm going to create a file called second file. Okay, this file is something I'm going to attach it to the second directory. Okay, I'm going to do new of git of file, and I'm going to name this as second directory file. And now what I'm going to do is I'm going to get second directory level +1 and pass second directory as the parent of this particular second file. Okay, with all files creation in place, what I'm going to do is I'm going to do root.of add child of file2. Okay, and I'm going to do second directory .of add child of second file. Okay, I'm attaching this, I'm attaching the second file to the second directory. Okay, and I'm attaching root.of add child of second directory. Okay, perfect. Now let's run it without the commit. Okay, and here we are able to see everything is under yellow, which means like none of this is saved. Now I'm going to run root.of commit. Perfect. Now run root.of status and print tree. Everything is saved, which means there are no changes in our file system. Okay, now what I'm going to do is I'm going to pick up file2, and I'm going to change the content. Okay, file2.of content I'm changing into some random text. Okay, now I'm without committing, I'm going to run root.of status and print tree. Okay, so what happens? Our git is intelligent enough again to find file2 is nothing but the file with hello world. Okay, it says the hello world content is changed, which is really good, right? So that is that is working perfectly fine. Now again I'm running git.of commit. Okay, now again I'm going to run root date status and print tree. Okay, now everything is under the saved state. So there are no yellow in the output. Now what I'm going to show you is what if user is going to save the file with the same content again. Do you think it's going to print with the yellow color? Let's quickly check that. Well, the answer is no, because remember, everything that we are taking the content and hashing is used by the SHA-256, right? And if you remember, SHA-256 is a one-way algorithm. For all the inputs of same content or same string, it is going to give you the same hash code, right? So since the file is again resetting with its own content again, our commit never changes. So that's it. I guess I would recommend students to add more files and more directories and play around with this code to completely get the gist out of it. Our mini git is of course sort of replicating the actual git, and in fact the real git uses Merkle tree behind the scenes. So we have implemented Merkle tree. We have used that Merkle tree to implement git in order to detect the file changes, right? So finally, in the last lecture, we will revisit our learnings and see where Merkle tree is used in other places. Thank you. And welcome to this lecture, Final Thoughts. So finally, we have learned in this course what is Merkle tree is all about. In this process, we have identified what is one-way hashing, and we have used the SHA-256 algorithm in our Merkle tree implementation. So we have written the whole Merkle tree from scratch, completely in vanilla JavaScript, In fact, this will allow the students to understand Merkle tree and its core concept of hashing and recursions in plain JavaScript. And finally, we have identified a use case of how Git identifies the changes in file, and we picked that problem and solved particularly with Merkle tree. In fact, as I said earlier in the lectures, Git uses a specified version of Merkle tree in order to solve this problem. Not only that, Merkle tree has other use cases, like they are used in Bitcoin. If you aren't aware of Bitcoin, Bitcoin is hottest topic in world of cryptocurrencies, where the whole transaction or the genesis block is completely made up of Merkle tree. All right, and apart from that, DynamoDB is world's famous NoSQL database from Amazon, and in order for the Amazon's DynamoDB replication to be happening, Merkle tree and Merkle proof are the algorithm that is used very vastly in DynamoDB. That's all. Thanks everyone. Thanks for watching this course. Kindly share it with your friends, since this course is going to be remain in Udemy. Share it with your friends, share your feedback, and thanks once again.